It started with a whisper in the dark, a subtle fading of light from one of the most iconic stars in our night sky. Then silence. For years, astronomers have closely watched Betelgeuse, that reddish glow marking the shoulder of Orion, a star both ancient and enigmatic. A red supergiant known for its unpredictable behavior, Betelgeuse has captivated scientists and stargazers alike. It's long been suspected to be on the verge of collapse, a ticking cosmic time bomb. But no one could say when until now. What the James Webb Space Telescope just captured isn't just data. It's a discovery so profound, so explosive, that it may well redefine our understanding of how stars die. And more than that, it could shake the very framework of what we thought we knew about stellar evolution. Because for the first time in human history, we have direct evidence, clear, undeniable, beautifully terrifying, that a supernova is happening in real time, not in some faraway galaxy, not as a ghostly remnant in our telescope's rear view, but right now, unfolding live, just 642 light-years away. Betelgeuse, a star more than 700 times the diameter of our sun and over 20 times its mass, is beginning its final act. This is not a simulation. This is not an artist's rendering. What Webb has captured is reality, the raw, unfathomable violence of a star tearing itself apart. It's as if we've been staring into the furnace of creation, and at last the door has swung open. The James Webb Space Telescope had been fixated on Betelgeuse for months, drawn by signs of instability that had been growing since its now famous dimming episode in late 2019. Back then, the world watched in wonder and fear as Betelgeuse darkened dramatically, an ominous sign that it might be entering the final phase of its life. Speculation ran wild. Was the supernova imminent? Was it days away? Weeks? Years? What no one could confirm then, we can now say with certainty, that moment in 2019 wasn't the end. It was the beginning of the end. Using its unparalleled infrared capabilities, Webb pierced through the dense stellar layers surrounding Betelgeuse. What it saw was chaos. Tremendous convective bubbles, each one the size of Jupiter, boiled on the star's surface before violently bursting. Plumes of gas hotter than anything found on Earth jetted outward at incomprehensible speeds. The light spectrum carried within it a chilling message. A shock wave was moving through the star's outer shell, a signature sign that the core had begun to collapse. This is the anatomy of a supernova, not described in textbooks, but observed live. We're seeing the precise, terrifying ballet of death. Core collapse, matter compression, and the outward push of stellar debris. And for the first time in the history of our species, it's happening close enough to witness with astonishing clarity. Unlike most supernovas, which occur in distant galaxies millions or billions of light-years away, Betelgeuse's detonation is close. Cosmically speaking, 642 light-years is a whisper. And that means two extraordinary things. First, its explosion will eventually become so bright that it could be visible during the day, brighter even than the full moon. Second, and more importantly, its proximity allows scientists to examine the death of a star like never before. Every step of this cataclysmic unraveling can be studied in detail. We're seeing how a star's core collapses under its own gravity, forging elements like carbon, oxygen, and iron in the crucible of destruction. These are not abstract concepts. They are the literal building blocks of life. You and I, the trees, the oceans, the air we breathe, we all come from this process. Webb's instruments have given us front-row seats to the event that makes existence possible. In a way, we're watching our origin story play out in reverse, a cosmic autopsy, if you will. Not just the end of a star, but the dissection of creation itself. What Webb is showing us is how planets form, how galaxies evolve, and how the elements that eventually become conscious beings are first born. But that's not all. The data Webb is pulling in isn't just for show, it's rewriting models. With this explosion, we can now simulate the final moments of other stars with unmatched accuracy. We can identify precursors, early signals of collapse, and potentially predict when other supernovae might occur. We're not just recording a death, we're learning how to see it coming. And the shock waves? They've already begun. Webb has detected high-energy particles rippling outward from Betelgeuse's core, slamming into nearby gas clouds and warping the intricate dust halo that surrounds the star. This is the aftermath of detonation, a cascade of chaos unfolding across light years, reshaping the surrounding interstellar medium. But what truly has scientists stunned isn't just the light, or the gas, or the radiation. It's the ripple in space-time itself. There is mounting evidence that Betelgeuse's collapse may have triggered gravitational waves, those elusive tremors in the fabric of the universe that Einstein predicted over a century ago, and which only recently have we been able to detect. If confirmed, this would be the first time a visible supernova has been directly tied to a gravitational wave signature. And that could change everything we know about how light, mass, and time interact on a cosmic scale. Then there's the big question: what's left behind? A neutron star? A black hole? Or something even stranger? Webb's data reveals irregularities. The collapse appears uneven. Parts of the star's material are being pulled back inward, suggesting an asymmetric explosion. There are magnetic field disturbances and plasma voids that defy current models. Some astrophysicists are daring to whisper a term once reserved for theory alone: transitional object. A new kind of remnant, one that sits between a neutron star and a black hole, one that, until now, has never been observed. If Webb has indeed recorded such a phenomenon, this would be not just a discovery, but a birth, the birth of a new class of cosmic object. And yet, despite the violence and enormity of it all, people want to know, are we safe? The answer is yes. Betelgeuse is too far away to pose any direct threat to Earth, but that doesn't mean it won't have consequences. The energy unleashed in a supernova is staggering. Gamma rays, charged particles, electromagnetic bursts. These waves can influence nearby star systems, change how cosmic dust behaves, and even distort the way we observe light from distant galaxies. In the long term, this explosion could subtly alter the way we perceive the universe. The Webb telescope is now watching closely, tracking how the radiation front expands and interacts with the broader galactic neighborhood. Because this isn't just an explosion, it's a ripple in the grand tapestry of everything, a disruption that could echo for millennia. And yet there is something poetic in the violence. A star, once brilliant and strong, has reached its end. But its death is not the end of the story. It is the beginning of something new. From the ashes of Betelgeuse will rise new stars. New planets may form in the cold wake of its fire. It is destruction, yes, but also renewal. And we were lucky enough, impossibly lucky, to witness it. As the James Webb Space Telescope continued its focused observation of Betelgeuse, what began as a monumental discovery soon turned into a full-scale cosmic unraveling. With every transmission, new data painted a more chaotic, more violent, and far more puzzling portrait of this red supergiant's final moments. What had started as a simple effort to monitor a dimming star evolved into a window through which humanity could peer directly into the mechanics of death and rebirth on an astronomical scale. But as the details emerged, the narrative began to twist, because what Webb found was not only unexpected, it was in some ways deeply unsettling. What Webb began capturing wasn't just a standard supernova process. This was something altogether stranger. Typically, in the death of a massive star like Betelgeuse, a symmetrical collapse forms a neutron star, or, in more massive cases, a black hole. But the unfolding collapse here wasn't behaving like any standard model. In fact, the light emissions coming from Betelgeuse had shifted in a way that defied expectations. Spectral analysis indicated the presence of strange asymmetries. One hemisphere of the star appeared to be ejecting material at a vastly accelerated rate, while the other remained oddly stable. This wasn't just an uneven explosion. It looked like the star was being torn in half from the inside out. At the center of this chaos, Webb's spectrometers detected a burst of exotic particles, particles that had never been observed in such proximity to Earth. Among these were high-velocity muons and something even rarer, unstable heavy baryons that, according to current understanding, should decay almost instantly after formation. And yet here they were, persisting longer than expected, flickering through space like echoes of forbidden physics. The implications? Either the extreme conditions inside Betelgeuse are bending physical law in ways we don't yet understand, or we are witnessing the kind of quantum chaos that typically only occurs at the edge of black holes. Further complicating the picture, Webb's deep field cameras identified strange voids forming around the star's outer shell, zones where plasma seemed to vanish rather than radiate outward. These zones weren't just empty, they were absorbing surrounding material. This effect, seen alongside the collapsing magnetic fields and distorted gravity gradients, strongly suggests that the collapse might not just produce a black hole, but something different, something transitional, a phase shift of matter not yet described in modern astrophysics. The collapse of Betelgeuse was no longer just a spectacular death, it was becoming a laboratory of impossible physics, and the clock was ticking. During this same observation window, another anomaly caught the scientific community off guard. Webb began detecting ripples in the fabric of surrounding space, small gravitational waves, not dissimilar to those measured by LIGO in the past. But these were different. They were localized, coherent, and came with high-frequency tremors that could only be produced by rotational collapse at speeds approaching relativistic limits. This meant that Betelgeuse's core wasn't just collapsing, it was spinning so rapidly as it shrank that its internal structure might be warping spacetime itself. The core, in its final act, could be transforming into something exotic, a quark star, or worse, a hypothetical singularity with properties unknown to current science. The consequence of this possibility couldn't be overstated. A singularity forming just 642 light-years away, however stable, would be the closest one to Earth in recorded history. While Betelgeuse's gravitational pull is not dangerous to our planet due to the vast distances involved, the observational proximity to such an event gives humanity the rarest of opportunities. We are standing on the edge of witnessing what lies at the boundary of known physics. The inside of a dying star is no longer a mystery. It is being broadcast to us in real time. As the supernova shock wave pushed outward, Webb's sensors picked up something even more alarming, an intense flux of gamma radiation, not in a burst, but in a sustained, pulsing rhythm. Gamma ray bursts, GRBs, are typically brief, lasting mere seconds or minutes at most. This one had lasted for over an hour before fading, something never seen before. The frequency and pattern of the bursts mirrored pulsar emissions, but were too irregular to be explained by a typical neutron star remnant. What was emitting them? One theory gaining traction is that we are witnessing the birth of a magnetar, a type of neutron star with a magnetic field so powerful it could erase data from hard drives from thousands of kilometers away were it close to Earth. Even more shocking is what lay in the ejected matter. Using spectral decomposition, Webb identified exotic elements that should not exist in detectable quantities, not in supernovas, not anywhere. Alongside expected elements like iron, oxygen, and carbon, there were traces of promethium, technetium, and even small quantities of transuranic elements, materials typically only formed in particle accelerators or nuclear detonations on Earth. The conclusion: Betelgeuse's collapse had reached energies and fusion states so extreme that it had crossed into an area of elemental synthesis previously thought impossible in nature. That discovery alone shattered assumptions. Elements like technetium have no stable isotopes, yet here they were, lingering in the debris field, held together perhaps by forces yet to be fully understood. Could the collapse of a massive star under asymmetric conditions be a forge for the unnatural? Are we, in a sense, seeing the cosmic version of a particle collider, only with mass, temperature, and magnetic forces no machine on Earth could ever replicate? If so, then we're not just watching a star die. We are watching the very blueprint of advanced matter creation. The implications for physics, chemistry, and even cosmology are staggering. Meanwhile, back on Earth, ground-based observatories began collaborating with Webb in a coordinated global effort to track the debris field. The energy signatures coming from Betelgeuse were already affecting telescopic sensitivity across the spectrum. Light from more distant galaxies was being filtered and refracted, through the expanding halo of superheated gas and plasma, warping observational baselines. For cosmologists, this meant recalibrating instruments, not just for Betelgeuse's immediate vicinity, but for entire sky segments, where its energetic footprint now bled through. And yet, it was becoming harder to ignore one final, disturbing possibility, that this event, though far, could alter the observational structure of our own solar system. The radiation burst from Betelgeuse, though unlikely to harm life on Earth, could potentially disrupt the heliosphere, the protective magnetic bubble surrounding our solar system. There were already early reports of anomalies in deep space probes like Voyager and New Horizons. Readings from their instruments showed minute but measurable increases in high-energy particle bombardment. If the radiation wave is as energetic as Webb's instruments suggest, these changes could last decades or even centuries. At the same time, Webb's long-term exposure revealed a feature that sent shock waves through the theoretical astrophysics community. A dark ring, circular, cold, and disturbingly uniform, was forming at the outer edges of the expanding explosion. It was absorbing light rather than emitting it. Dubbed the Betelgeuse void, it defied current understanding. Some scientists speculated it might be a photon trap, a naturally forming lens of warped space. Others fear it could be a precursor signature of a gravitational collapse in progress, where the escape velocity had crossed the speed of light, not fully a black hole, but close enough to signal that the surrounding space was folding inward. This wasn't just a supernova anymore. It was an anomaly field, a region of space no longer behaving the way space should. And in that silent, expanding chaos, we were left to confront something more profound. A star, familiar to ancient civilizations, whose name is recorded in myths, telescopic logs, and the poems of stargazers across centuries, was no longer the same. Betelgeuse, the guiding fire in Orion's shoulder, was disappearing, replaced by a rift of light, a library of cosmic physics, and a mystery that even the most powerful observatory humanity has ever built cannot yet explain in full. In the days and weeks that followed the detection of Betelgeuse's cataclysmic transformation, the James Webb Space Telescope transmitted data that didn't just raise questions, it shattered confidence in long-held theories. The cosmic event unfolding before us was no longer being treated as a singular stellar death. It was now an astrophysical crime scene, a cosmic riddle unfolding in real time. And the instruments of the most advanced space observatory ever built were racing to keep up. As the dust cloud expanded, Webb's mid-infrared sensors began capturing bizarre emission structures in the surrounding space. These weren't random plumes or jets. These were ordered, lattice-like formations in the ionized gases, extending outwards like ribs spiraling from the central mass. At first, astronomers thought they were seeing echoes, reflections of the original shock wave bouncing through interstellar dust. But the formations held their shape far too long. Webb's imaging suggested a framework, almost like a skeleton formed from highly energetic magnetic scaffolding. Some researchers began whispering comparisons to Dyson structures, not because Betelgeuse had anything artificial about it, but because the energy dispersal patterns looked eerily engineered. And if they weren't artificial, then something about the laws of energy distribution in supernovae needed a complete rewrite. But just as the scientific community was beginning to get its bearings, another complication emerged. The gravitational lensing effects around the Betelgeuse void were increasing. This meant the space itself, around the former star, was becoming heavier, denser, and this gravitational distortion wasn't evenly distributed. Instead, there appeared to be a drift. A slow, spiral descent of nearby interstellar dust into the blackened ring, as though something inside was pulling not radially, but rotationally. This spiral pattern implied more than collapse. It hinted at accretion, a slow rebuilding of structure from within the core, as if Betelgeuse was not dying, but reassembling itself into something unrecognizable. And then came the radio signals. Webb doesn't detect radio waves, but coordination with Earth-based observatories soon picked up faint emissions pulsing from the direction of Betelgeuse. These were not typical radio emissions from magnetars or pulsars. Instead, they came in staggered frequencies that shifted over time, each burst echoing a pattern but never repeating. A form of fractal time signature was embedded in the static. While most experts dismissed any suggestion of artificial origin, others noted that this pattern mirrored those seen in quantum entanglement resonance, suggesting Betelgeuse's collapse may have triggered quantum-scale coherence at interstellar distances. In less speculative terms, the star might be sending out signals, not intelligently, but as a function of its collapse, containing information in the energy structure itself. What if, instead of just blowing apart, Betelgeuse had reached such extreme states of mass-energy transformation that it crossed the threshold into what some theorists call a post-matter condition, a state where space-time, energy, and quantum information begin blending? Some physicists believe that such a transition could allow information to travel without degradation, effectively transmitting the last moments of Betelgeuse's existence across the galaxy, embedded in its very collapse. If this proves true, it would be the first time a stellar body has not only died, but sent out a natural signal containing the physics of its own death. A kind of stellar autobiography written in radiation, gravity, and light. Back on Earth, this possibility has triggered a cascade of new initiatives across observatories, quantum labs, and AI-driven data mining operations. Already, machine learning models have been deployed to decode the signal patterns, searching for any embedded constants or transformations that might reflect a previously unknown law of nature. While most remain skeptical of anything more exotic, the fact remains. Betelgeuse is not behaving like a dying star. It is behaving like a puzzle, and not just to scientists, but to instruments themselves. In an unprecedented event, even the instruments aboard Webb began reporting telemetry issues, delays, surges in energy readings, and inexplicable spikes in background noise when pointed at the Betelgeuse void. Engineers insisted there were no malfunctions, but the data stream was growing chaotic whenever the telescope locked eyes with the central remnant. The official explanation was electromagnetic interference from ionized gas. Yet the deeper fear remained unspoken. What if the laws near Betelgeuse were no longer constant? What if space itself was changing? These concerns weren't helped by the final image packet received from Webb's long-range imager, just as the core became obscured. In the final deep field exposure, a faint object appeared at the heart of the void. It was neither star nor planet. It had no thermal signature, no X-ray emissions, and no discernible mass. And yet it reflected light, a tiny glimmer, symmetric, focused, and alien to any known natural process, hovering at the edge of the void like an eye-opening within the storm. Webb's computers tagged it as Non-Catalog Reflective Object A, designation Betelgeuse Central. But among researchers it was given a different name, the artifact. Immediately debate erupted. Was it a sensor error, a cosmic mirror effect caused by warped gravity? Or had something formed in the final seconds of Betelgeuse's collapse that defied categorization? Theories ranged wildly. Some proposed a quantum knot, tightly bound space-time, curled into a stable loop. Others feared it might be the birth of an artificial horizon, a bridge point between dimensions, or even the first naturally occurring Einstein-Rosen bridge, a wormhole. None of these could be proven, but none could be ruled out. And that was the problem. Webb had revealed more than science could immediately answer. But perhaps the most emotionally charged revelation wasn't in data. It was in the simple human realization that a fixture of the night sky, visible to our ancestors, sung about in ancient poetry, and charted by Babylonian astrologers, was gone. Betelgeuse, the burning shoulder of Orion, had collapsed into silence. In its place, we were left with a ghost, an echo made of light, distorted by its own demise, now drifting ever outward. And yet, within that ghost lies hope. For while Betelgeuse's death marked an end, it also marked a beginning. The very dust now pouring into space will, over millions of years, cool and congeal. It will seed nebulae. It will help form new stars, possibly new planets, possibly new life. The hydrogen and helium forged in its belly are not lost. They are recycled into the galactic engine. The ashes of Betelgeuse will one day become the cradle of someone else's sky. And perhaps most powerfully, the event has forever changed how we perceive our universe. Never before have we watched a star die in real time, with such clarity and from such a close cosmic distance? Never before have we received a front-row seat to the very moment when the boundaries of light, gravity, time, and matter break down and rebuild. For the first time in human history, a telescope didn't just show us what was out there. It made us feel what was out there. It connected the incomprehensible violence of a supernova to the quiet, poetic impermanence of all things. It showed us the power of observation, not just to see, but to understand, to feel awe. Betelgeuse didn't just explode. It became a teacher, a warning, a mirror. And in its final act, it gave us the rarest of gifts: truth without ambiguity, light without boundary, wonder without end. And so now we wait for the next star to fall, for the next anomaly to speak. Because somewhere, beyond the veil of visible space, more secrets are waiting. And thanks to the James Webb Space Telescope, we now know how to listen.